Welcome to Springs Fundamentals 101. My name is Gary Van Buren, your instructor for this session. This class is designed as an introductory class on springs and will describe the different types of springs produced and describe the additional training modules available from the Spring Manufacturers Institute for each spring type. This program was developed by the SMI Technical Committee, and I hope you enjoy the session. The goal of the Spring Manufacturers Institute is to serve, support, and educate North American precision spring manufacturers in their pursuit of competitiveness in world markets. First, a few words about SMI. The Spring Manufacturers Institute was founded in 1933 by Associated Spring. SMI is an association of companies that manufacture springs and their associate suppliers. The members of SMI work together to meet the key issues of the industry worldwide, such as quality, materials, technology, and government regulations. SMI provides many services, including a quarterly magazine, Springs, a variety of technical publications, spring design software, industry data, seminars, meetings, safety and regulatory compliance information, and technical assistance. The Springs magazine is available in a digital format and can be searched for articles of interest. The goals of this module are: present an overview of the spring design training program, describe the 7-step spring design process, answer the question, what is a spring? Describe the common types of spring configurations, discuss spring materials, define common spring terminology, and describe reference materials. First, I will present an overview of the spring design training program. This slide presents a colorful view of the different types of springs that we will discuss today. The photo is from the Myers Spring website. Springs are made in many types, shapes, and sizes ranging from delicate hairsprings for instrument meters to massive buffer springs for railroad equipment. The majority of this module discusses the relatively small springs that are cold wound from wire. Wire can be round wire, shaped wire, or flat strip. Chemical composition, mechanical properties, surface quality, availability, and cost are principal factors to be considered in selecting materials for springs. The SMI Spring Design Training Program is organized in 3 course levels: Fundamentals, Basic, and Advanced. The target audience is shown for each course level. Notice the arrow and the note, "You are here." This is where we currently are in this discussion. On this slide, the subject of each course is presented. There are 3 fundamental modules, 6 basic modules, 4 advanced modules. Please note the course description on the right. The top 3 are for the non-engineer, like salespeople, secretaries, and others who are not involved with spring design. The next 6 are for those who work directly in engineering or with customers whose spring designs are reviewed for manufacturability. The last 4 will involve engineering, quality, and those who work on more than just design. On this slide, course details are presented for basic modules 201 and 202. 201, compression spring design. 202, extension spring design. Each module is planned as a 4-hour session and will include examples for completion by each student using the ASD7 software. All aspects of spring design will be discussed in these classes. Information ranging from the proper material to choose, safe stress levels, fatigue, and of course, cycle life. On this slide, course details are presented for basic modules 203 and 204. 203, torsion spring design. 204, spring washer design. Each module is planned as a 4-hour session and will include examples for completion using the ASD7 software. And as stated on the previous slide, we will discuss information ranging from the proper materials to choose, safe stress levels, fatigue, and of course, cycle life. On this slide, course details are presented for basic modules 205 and 206. 205, beam and torsion bar spring design. 206, snap ring design. Each module is planned as a 4-hour session and will include examples for completion using the ASD7 software. And as stated on the previous slide, we will discuss information ranging from the proper materials to choose, safe stress levels, fatigue, and of course cycle life. On this slide, course details are presented for advanced modules 301 and 302. 301, springs, fatigue. 302, springs, heat treatment, and high temperature alloys. Each module is planned for a 4-hour session. Module 301 will include examples for completion using the ASD7 software. The names for these two courses make them pretty self-explanatory. On this slide, course details are presented for advanced modules 303 and 304. 303, springs, corrosion-resistant alloys and finishes. 304, springs, dimensioning, tolerancing, and testing. Each module is planned as a 4-hour session and will include limited examples for completion using the ASD software for the Course 304 module. In the Class 303, we will delve into many types of materials and finishes best suited for your customer's needs. In the Class 304, we will discuss what dimensions should and should not be toleranced, where these tolerances come from, and how they may be tested. I will now describe the 7-step spring design process. The first 3 steps, define the problem, select spring configuration, and select material, are critical to designing what the customer desires. Select stress levels and design optimization are iterative steps that refine the design. Check design and specify are steps that lend themselves to finalizing the advanced product quality planning protocol. I will now address the question, what is a spring? A mechanical spring may be defined as an elastic body whose primary function is to deflect or distort under load and which recovers its original shape when released after being distorted. Springs are flexible members that store energy. The amount of energy a spring can store is a function of the strength of the material the spring is made of. At this point, I will now discuss the common types of spring configurations. This is step number 2 of the 7-step spring design process. On this slide, we show the 3 most common types of springs along with the relative motion of interest for each type. Compression springs are used to resist pushing forces. Extension springs are used to resist pulling forces. Torsion springs are designed to work over an arbor and resist a force that causes the spring to wind or twist. This slide shows the specific training modules for each of the 3 spring types. Spring Design 201, compression springs. Spring Design 202, extension springs. And Spring Design 203, torsion springs. This slide is similar to the previous slide, but shows additional spring types and the training modules where they will be covered. Various designs of helical compression springs are shown on this slide. The conical, top left, just below that's the hourglass. The center is the constant pitch, which is the most common spring made today. Then the top right is the barrel, and the bottom right is the variable pitch. Compression springs can provide a wide range of deflections with either constant or variable rates. Conical springs offer lower solid height capabilities as well. Automotive applications of springs include valve springs, suspension springs, transmission components, seatbelt retractor springs, and more. Certification to the International Automotive Task Force Quality System Standard 16949-2016 is required. Just for fun, For the driving enthusiast, the California is Ferrari's front-engine, 4-seat retractable hardtop GT. This is the most relaxed, civilized, and affordable car in the Ferrari lineup. But with over 500 horsepower and a top speed of nearly 200 miles per hour, the twin-turbo V8 California T is respectable. Direct fuel injection, a 7-speed dual-clutch transmission, which replaced the abrupt single-clutch gearbox used in other Ferraris of the era, retractable hardtop, and a truly comprehensive launch control system. It's even had unique stacked exhaust pipes to help reduce high-speed lift at the back end of the car. Persistent rumors said the California was originally conceived as a Maserati, but the car's performance dispelled any doubt about the California's credentials. Notice the cost of the springs. They are available for a mere $1,450. A slightly different spring design is used on the Porsche 911 Carrera S, and they are offering a whopping 63% discount on these springs to lower the car 1/2 of an inch. Oh, and don't forget the sunglasses. Aerospace and defense applications require a higher level of certification to standard AS 9100 Rev C. Compression springs are covered in Spring Design 201. Bevel washers and disc springs are covered in Spring Design 204. Garter springs are helical extension or compression springs whose ends are connected so that each spring becomes a circle and exerts a radial force. Their primary applications is in oil seals. There are other uses also, including small motor belts, electrical connectors, and piston ring expanders. Retaining rings and snap rings are covered in Spring Design 206. They are mainly used to locate or retain parts on shafts or in cylinders. Many types of retaining rings can be found in hydraulic connectors. Flat spiral springs, power springs, and constant force springs are shown in this slide. Coarse materials are currently being planned for these types of springs. These photos are courtesy of Associated Spring. Beam and torsion bar spring design will be found in Spring Design 205. Simple beam or elliptical springs will be discussed in Spring Design Class 205. Simple beams are usually rectangular in shape and formed into an arc as illustrated here. Load is usually applied at the center of the arc. For the purpose of classification, flat spring refers to springs made from sheet, strip, or plate. Flat springs may contain bends and complicated forms, and many times will be formed in a stamping press. These will be discussed in Spring Design Class 205. Returning to the 7-step process for spring design, let's take a look at defining the design problem. Many designs do not perform well in service due to incomplete or unclear definition. That is why this step is so important. The basic assumption is that the spring designer knows both the spoken customer needs and the unspoken customer needs. Let's look at the spoken customer needs. Functional requirements, space limitations, environment, service requirements, special considerations. And now the unspoken customer needs. Lowest cost, manufacturability, general tolerances, never rusts, never breaks. This slide provides definitions of the spoken customer needs. Let's review. Basic assumption, the spring designer knows. Functional requirements, expressed as a load at test position and or spring rates. Space limitations, defined by describing the envelope in which the spring is expected to operate. Environment, the operating temperature and a description of substances in contact with the spring. Service requirements, expected life, frequency of loading, rate of loading, and permissible relaxation. Special considerations, restrictions due to assembly, Electrical conductivity or magnetic requirements. There is a key point here. In order to make a cost-effective design, it is essential to have the design problem clearly defined. Next, we will discuss spring materials. This slide shows the step we are in for material selection. This slide emphasizes that material selection is often dictated by experience or the particular application. With regards to selecting the stress level, it is important to know if the spring will operate in a static or dynamic condition. Is it prone to fatigue? Or is it a safety critical application? With regard to material selection, engineering factors such as the operating environment, stress conditions, fatigue conditions, static and dynamic. What do we mean by static and dynamic? For a static condition, think of a pressure relief valve in your hot water heater. It is normally cycled only one time. For a dynamic condition, think of your car. You want the valve springs in your car's engine to cycle billions of times without failure. There are other factors to consider when selecting material, and they are commercial factors such as cost and availability. What is a spring material? High-strength alloys ranging from medium and high-carbon steels to beryllium copper depending on the need of the design, from quench and tempered, cold worked, and precipitation hardening processes. Ideally, they have high strength, a high elastic limit, and a low elastic modulus. How are spring materials classified? Carbon steel wires, alloy steel wires, stainless steel wires, copper-based alloy wires, nickel-based alloy wires, cobalt-based alloy wires, titanium alloy wires, carbon, stainless steel, and copper-based alloy strip. This follows the organization of materials presented in the Advanced Spring Design Software, ASD7, that I will discuss later in the presentation. As this is an introductory class, our focus will be on wire products versus strip. We will now move forward to define common spring terminology. Special terminology has evolved in the spring industry to describe features of helical compression springs. Several of these terms are defined, and the relationship between terms is shown here. Communication between designer and spring maker is improved if these common terms are used. Additional details can be found in the Spring Design 201 module and the Encyclopedia of Spring Design. Free length is the overall spring length in the free or unloaded position. If loads are not critical, free length should be specified. When definite loads are required, free length should be a reference dimension that can be varied to meet load requirements. Solid height is the length of the spring with all coils closed. Terminology has been created over the years in the spring industry, which is commonly used in spring design. For instance, notice on this graphic we have an OD/ID shown to the right. This is outside diameter and inside diameter. And on the left we have the free length, mean diameter, wire diameter, and pitch. These are all very common terms used in our industry that you as a student should become familiar with. A helical compression spring can be either left or right hand coiled. If the index finger of the right hand can be bent to simulate the direction of the coil so that the fingernail and coil tip are approximately at the same angular position, the spring is right hand. If the index finger of the left hand simulates the coil direction, the spring is left hand wound. Another way of saying it is if the coil direction of the spring is clockwise, the spring is right hand wound. If the coil direction of the spring is counterclockwise, the spring is left hand wound. Type of ends available are plain ends ground, squared ends, and squared ends ground, as shown in this graphic. To improve squareness and reduce buckling during operation, a bearing surface of at least 270 degrees is required. Squared and ground ends are normally supplied with a bearing surface of 270 degrees to 330 degrees. Too much grinding can result in thin sections. Squared ends only are preferred on springs with small wear diameters, 20 thousandths of an inch or less, or a large index, something greater than 12, or a low spring rate. Squared ends cost less to manufacture than squared and ground ends. On a side note, it is not common to have open springs with ground ends. The total number of coils, N sub T, should be specified as a reference number. The number of active coils, N sub A, will be different depending upon the type of N. The table below shows the relationship between the total number of coils, N sub T, and the number of active coils, N sub A, by N type. The spring rate for a helical compression spring is defined as the change in load per unit deflection. It can be thought of as a measure of spring stiffness. Spring rate may be shown as a rate or gradient in units pounds per inch or newtons per millimeter. When necessary to specify a spring rate, it should be specified between two test heights which lie within 15 to 85% of the full deflection range, as shown in this example. The dimensions of interest in an extension spring are shown in this slide. For instance, free length of an extension spring is the distance between the inner surfaces of the ends. An important parameter of an extension spring is the initial tension. Initial tension is the amount of force required to begin the initial deflection. Additional details will be covered in the Spring Design 202 module. There are two common types of extension spring ends. Machine hook or German hook, also known as the full twist loop, pictured top left. Extended hook is in the top middle, and a half hook top right. Crossover center or English loop is on the second line. The balance shown can be made, but normally at a higher cost. Additional information will be covered in Spring Design 202. The tight wound torsion spring pictured here is the most common type manufactured for today's marketplace. The double torsion is also quite common. Many end configurations are available, yet cost will increase with complexity. Additional information will be covered in Spring Design 203. Finally, we have arrived at the last topic in this module, reference materials. The SMI Spring Design Training Program is based on two sources, the SMI Encyclopedia of Spring Design and the SMI Advanced Spring Design Software, otherwise known as ASD7. The Encyclopedia of Spring Design is a 4-volume set available from the SMI online store. The SMI Encyclopedia of Spring Design is also included in the ASD7 software. The book, Mechanical Springs by A.M. Wall, is also available at the SMI online store. This is considered by many spring makers as the Bible of the spring design. Live ASD7 software demonstrations are provided for both existing customers and new prospects by Universal Technical Systems, free of charge via GoToMeeting. Presentations typically take about an hour. For more information, please contact Todd Pfeiffer. Todd Pfeiffer is one of the smartest people we know. He is an excellent resource you should get to know. Thank you for your attention. I hope that you found this webinar to be of interest, and I hope to see you at a future SMI basic or advanced training session. If you have any questions concerning this webinar, please contact the Spring Manufacturers Institute at www.smihq.org.